So if you want to talk about step 4, I guess, step 4 is to get the total current. The whole reason you're condensing the resistance down to such a summative value is to get an understanding of the total resistance presented to the flow by the circuit. And that's going to determine how much current flows overall. Now we just did that hard work to put all the entire circuit down into a single resistance. We're going to take it all back apart again. Okay? So step 5 is to take it back apart to get the individual currents and voltages across each element. So here is the method I'm going to suggest for this. I'm going to suggest that we make ourselves a little chart so we can keep track of who we got and who we didn't. So for resistor 1, resistor 2, resistor 3, resistor 4, we want to get the current through each one and the voltage drop across each one. All right? So that chart will help me organize my information, and this voltage waterfall here is going to be really worthwhile. It's going to let us kind of, by deductive reasoning, figure out how to progress through. Okay? So there's always got to be somewhere that you can start. So one of these values is going to be something that you already know. Okay? In my case, I already know the current through resistor 1. Why is that?
Same as the total.
It's the same as the total current, right? This was before any forks happened. So whatever the total current is has to all go through R1. So in my case, I know from my I total value, that goes right in here, 0.243. And let me put the units in the header so I don't have to put them on everything. 0.243 amps or 243 milliamps. So here's the thing. Once you know one of the values in a row, you know the other because of Ohm's law, right? So I know the resistances of all of them. And so if I know the current or the voltage, I can get the other, right? So let's go ahead and do that. I guess let me put it over here. Where do I have room? I guess I'll go over here. So V1 equals I1 times R1. So I've just figured out that 0.243 amps goes through that resistor, and that resistance value itself is 20 ohms. So if I multiply those two together, I'll get something on the order of 4.9. So 4.9 volts drops across resistance 1. Please note, it is not 12. Okay, 12 is the entire journey from top to bottom. I don't know what it is about students. They can combine into an equivalent resistance, but then once they get that, they just take the 12 volts and divide every resistor by that to get the current or something like that. That doesn't work, okay? The drop from here to here is 4.9 volts. We're just getting started. This whole drop is 12 volts, but you only drop 4.9 volts of it going from A to B. So that's just the top step in our waterfall. Now, we have to figure out, I've got the first line completed, the first row. I need to leverage something to get onto one of the other rows. Question?
All right, so you just talked about the E and the voltage drop. I had that question, I was waiting for it. So the E comes from the battery.
Yes, and that's reserved, that's a special character that's reserved for the entire journey from top to bottom.
And the voltage drop
Across a given resistor, yes.
going through the resistor.
That's right. So each individual resistor has its own voltage drop. That may be just a part of the entire journey, right? So we have that the 12 volts from A to D is split up in a number of different ways because you're dropping through a number of different resistors which all have their own voltage drop.
Okay, so when you're talking about the, when the resistors are arranged in parallel, and you say the voltage drop is the same,
In each one of them.
so you mean like the voltage difference dropped through the resistors are the same?
Yes, whatever that is, yeah. So for instance, we said that this V2 was in parallel with the 3-4 combination. So that means that whatever this voltage drop is going to be the same for both of those.
So what about if the total resistance is different in those two resistors in parallel? Would your voltage drop still be the same?
Yes, that's the whole idea of a parallel, right? The parallel, the whole idea is that you give different options to go between the same two voltage places. The current may be different, that's the whole deal with parallel, right? The voltage drop is the same, but if the resistances are different, then more current will go through the easy way. But the whole definition of parallel is you're connecting the exact same two places, same voltage drop. The currents may be different through each option, but the voltage drops are the same. Okay. So we know the current going through this one, A to B. That's to the 243 milliamps. Can we just say it splits into two? Definitely not. In fact, let's look at it conceptually. R2, that's 40 ohms. So that's a 40 ohm branch. Actually, we will combine them in parallel here. We have a 40 ohm branch and a 110 ohm branch, right? Current is not going to split through those equally. It's still the same journey from B to D ultimately. So same voltage drop. That's what we said right here. The voltage drop across 2 and 3 and 4 are the same. But the currents are not going to be the same. More goes through the easy way. More is going to go through the 40 ohm and less is going to go through the 110 ohm. So that's not going to work. We don't know how much of the current, we found the total current, but we don't know how much of it goes into each fork. But we do know a voltage value of one of the other resistors. Which one is it? V2, because we know this whole drop is 12 volts. You drop 4.9 across here, and you have an option to go all the way down by going to resistor 2. So resistor 2, we can just simply say that these two combined have to give you 12, your 12 volts, right? So we know that the entire journey from top to bottom was 12 volts. We know that the drop through resistor 1 is 4.9, and we know that we can finish the job by going through resistor 2. So we solve here for resistor 2, and resistor 2 comes out to be what, 7.1, I think? Yeah. That's 7.1 volts. .1 volts. Put that in the diagram here. 7.1 volts. So we can label that here. And again, that was easy to notice because the voltage schematic basically lets kind of think of it as lengths here, right? So we make sure that this length plus this length equals this length. Now let me ask you this. If you have a 12 volt drop, why wasn't the drop 6 volts and 6 volts? Why didn't it split off in unequal pieces, 4.9 and 7.1? Why did that happen? Different resistances. What were the two resistances? They're right here. This belongs to that one, I guess. So the two resistors were 20 ohms and 29.33 ohms, right? That's what these two. So we always said when you have two things in series, this one has a larger value, it's going to get larger voltage drop, and that's what we see. All these conceptual things are present in this larger circuit. So that's why the voltage drop split up that way. It wasn't 6 and 6 volts to make 12. You can get that if the resistances in the series happen to be equal. But if one resistance in the chain has more resistance, it'll take more of the voltage drop. It'll hog more of the voltage drop. Remember, that's the deal with series, is that you got to pay more attention to the bottlenecks. And the bottleneck in this system is the 2, 3, 4 combination. Okay? It has more resistance as a whole than the R1 does. Okay? All right, so let's keep going. Well, now we've got one value in this row, we can fill in the other one, right? Once you have one, you get the other. So where do I have room for that? I guess I'll put it over here. So I2 is going to be V2 over R2. So I know that there's a 7.1 volt drop across R2, and the resistance was 40 ohms. And I can solve here and get the current that goes through that one. That current is 0.178 amps. I'll fill that in here in SI units.
Is V2 squared?
No, it's just V sub 2.
Okay.
It's the second resistor.
It's just, oh, that's for power. Okay.
I'm not computing power, I'm just computing current. So just an inversion of this for current. So I have 178 milliamps through this one. All right, so another row done. Now we have to again see how we can leverage that information to keep on progressing. There will always be a way. Now, I figured out that this was 7.1 volts, right? Can I just take that and divide it by 2 and then V3 and V4 are each half of that? No, you could if what was true?
The resistance.
They were equal resistances, but they're not. R3 and R4 are not equal resistances. So again, we learned that if they're in series, yes, it's going to add up to 7.1, but they're not going to equally add up. Okay? So we're going to find again that the larger resistance in the chain, in this case the 80 ohms, takes more of that 7.1 volt drop, and this one takes less, the R4, right? So we can't do that. Let's go to the current. Okay? So how can I get the current that goes through that branch? That's right, because all the current in the other branches are accounted for, so we can deduce how much flowed into the last branch. That total current forks off. Part of it goes through resistor 2, and the rest goes through 3 and 4. That's the junction, or I haven't called it a junction yet, but it's the fork in the road in equipotential region B. The current, which was, I guess I'll do it at milliamps, because I just like it better. So we had 243 milliamps of total current. That was what came from the overall resistance of the entire circuit. We found 178 milliamps went through this way. So we can figure out how much must have gone the other way, because you can't just, of course, have the charge disappear. So if you have a river that forks off, you know how much went in one branch, you know how much was left to go to the other branch. We can solve for this, I34, and that comes out to be 65 milliamps, or 0.065 amps. Fill that in over here. Actually, before I even do that, why is this so small? Why did such little current go over this way?
More resistance.
More resistance, exactly. So if you have two things in parallel, of course, more goes to the easy way. We had the two branches. R2 was 40 ohms, and then this was way harder, 110 ohms. No wonder so little current went through that branch. It's just a lot more resistant. So what happened was that this 243 milliamps overall split highly to one direction to go through the easy way, and then only a very small amount of it went through the hard branch. Does that make sense? Okay, so we'll fill that in over here. We have 0.065, and that's actually nice. I can just copy that because they're in series. So once you committed to that branch, you had to finish that branch. So now we're good to go, because of course, once you know the value in a row, you get the other one. So we can just finally compute. Where do I have room left? I guess I already did the strategy, so I can encroach on that one a little bit. So now we just finish it off. We want V3 equals I3R3, and V4 equals I4R4. So we put in the same current. In fact, this is redundant because these currents are the same. 0.065, 0.065. And we multiply them by each of their resistances, 80 ohms and 30 ohms. And we get 5.2 volts and 1.9 volts. What should those add to? 12. 7.1, right? Remember, this was an option to go here. So you can go drop down 5.2 volts and then 1.9 volts, right? That's an alternate way of dropping down the 7.1. So, you can always close your loop at the end, and if you find that that doesn't add up, you did something wrong, okay? So these should add to the voltage drop across resistor 2, which is 7.1, because resistor 2 is in parallel with the 3-4 combo. And again, why does it split up so evenly? Why is this resistor, V3, why is it more voltage? More resistance, exactly, right? This was 80 ohms, this was 30 ohms. So that's how you do it. This is a combo circuit. You have, I think, at least 3 or 4 of these on your homework, and this will definitely be on your exam. So make sure that you can go through something like this. Okay? Are there any questions on this? So you'll find as you do these, they are not that hard. It just requires being organized. I'm giving you the tools to organize. Oh, I guess I should finish off my graph, my chart here, 5.2 volts and 1.9 volts. Make yourself a little chart to fill in. Make yourself a nice little voltage waterfall. Circle your equipotentials, all that stuff. And it's really, you'll find, not too bad. Okay? It's a very kind of workmanlike skill. Not a lot of surprises can happen. Question?
Okay, all right, so back to the I total equals I2 plus I, the current 34.
Uh-huh.
So we're looking at I2 and I34 are parallel.
So I'm looking at this current flowing into this spot and then splitting off into those two currents.
So that makes it parallel. So, okay, so I.
So, well, I mean, it's not even, I'm just basically looking at the fact that charge flows in here and splits off into two things, and everything has to be accounted for, right? That's what current is. It's charge for time. So you can't have electrons just blinking out of existence. You have to, it has to go somewhere, right? So whatever electrons course into that fork, they have to come out. They have to choose a path. They can't just disappear. Are there any other questions? Yeah.
So in V2, so V2 is parallel to V3 and V4?
Well, it's parallel to the 3-4 combo.
Yeah, 3-4 combo, I'm
Yep.
sorry. And say, for example, V3 and V4 were exactly 1/2 length distance. So the length is equal, V3 and V4. Can you say?
You mean like these two?
Yeah, those two are equal.
So they split this to
Yeah.
whatever, 3.55 or whatever, yeah?
You can just divide that and just get the.
If these two resistances
Yeah.
are equal, then yeah.
Yeah, okay.
Yeah, you can always take shortcuts. So, for instance, when I say things like voltage isn't the same in series, they're not the same in series generally speaking, right? If the
Yeah.
resistances aren't equal, then they won't be equal. But you can always have the special case that you get lucky that the resistances are equal, then they just each take half the voltage drop.
Okay.
Likewise, if you have two resistors that are identical and parallel, then yeah, they even just take half the current, right?
Okay.
So these are shortcuts you can use. It's just, make sure you know when it's appropriate.
Thank you.
Any other questions? Okay, so just a little bit of cleanup on homework number 3. I want to talk a little bit about measurement devices. So, measurement. I think the easiest one to start with is a device called an ammeter. It measures electrical current. I'm sure it got called an amp meter at some point, but the P is kind of awkward, so it kind of got smoothed out of there. Okay. Its whole purpose is to measure current. Now it's easy to think in our modern technological age that these things are just magic boxes and not wonder too much about how they work. But the thing to understand about measurement devices is that they are just special resistors. What they are is a resistor. Normally, if you have something going on with the resistor, you have no way of knowing what's going on inside there. You can look at the power dissipated and say, oh, it's bright, if it's a light bulb or something like that, where the power dissipation makes it hot enough to glow. But you have no direct means of knowing what's the current going through that, or what's the voltage drop going across that, because there's no outward sign of what's going on with that resistor. Well, these measurement devices have a mechanism by which whatever's going on inside them, they output that in some kind of way. So we'll get into the mechanism a little bit about how that works. How is it that it can somehow signal what's going on inside? But that's for later. Right now, I want you to understand that their function in the circuit is no different than any other resistor. For instance, an ammeter measures the current through itself. That is what an ammeter is reporting. It does not necessarily can read your mind when you put it into a circuit. It has no idea which thing you want to measure the current through. It just really measures the current through itself. So you have to leverage that in such a way that it provides useful stuff. And here's what you do. You put it in series, you place it in series with the resistor of actual interest. You're exploiting the idea that resistors, when they're in series, they have the same current. So when the ammeter measures the current through itself, it's also by proxy measuring the current through something that you're interested in knowing, right? Does that make sense? So if you have, say, a resistor somewhere in your circuit, I guess let me draw in a circuit that's not something like this. So we have, I don't know, let's say something like this. R1, R2, R3, okay? So there's your circuit. If you could magically know what the current was, then you wouldn't need a measurement device. You would just, read the mind of the circuit and you know what's going on. But let's say you were interested in measuring the current through resistor 2. So the current, this is I1 or I total. It splits off. Some of it goes through over here. Some of it goes through over here. And let's say you are interested in knowing what is the current just through the fork of resistor 2. Well, here's what you have to do. You have to, somewhere along that fork, you have to put in an ammeter that will be in series with this. So here's what you do. Here's one option. You put a break in the circuit. Notice it requires breaking the circuit and putting into the main flow this device called an ammeter. And you make it flow through there. So basically, you're going to count the current right before it goes in through resistor 2. The ammeter will report the current through itself, and that happens to be exactly the same current that's just about to go through resistor 2. So that's a useful readout of I2. I'll give you another option. Anywhere along that branch is fine. You can put it after you'll count the current right after it passes through R2. The only thing you have to make sure is, of course, you don't put it somewhere else, because if you put it somewhere else, you'll measure I1 or I3 by accident, and you're trying to measure I2. So you have to put it in series, direct series, with the resistor of interest. Okay? So if you're doing this in lab, and if you haven't yet, I'm sure you will, remember, you need to put a break in the circuit so that current can't get to that branch at all, and then somewhere in the main flow, you need to put, either just before or just after your resistor of interest, you insert this ammeter. Okay? So it requires that you break the circuit and you place an ammeter in the main flow. Now I do want to point out something, is that if you start adding an extra resistance into the main flow, what's going to happen to the overall resistance of the circuit? It's going to increase. R equivalent